Hi, thanks, thanks for the introduction. Nice introduction. Good. Okay, cool. So yeah, so if there are any questions along the way, I'll also try to answer them. I think you should be good time-wise. So I'd like to get you in a little different frame of mind, maybe, and see if that works. So one of the ways we typically handle uncertainty in the world is to try and add structure, right? So if you think about autonomous driving, like the previous speaker's example, flying, all these things, you're trying to add structure that removes uncertainty, that increases reliability in the system, right? So the cases that I'm excited about, that I'm excited in, are cases where there's a lot of uncertainty, right? Imagine you're in tunnels, you're off-road, all of these situations, right? So you're essentially removing structure, and now your system has to be able to handle these situations, and that's a much harder case and requires your system to have more autonomy rather than automation. Just to put this in context, here's an example from the Dartmouth Subterranean Challenge a couple of years ago. So the robot had never seen this environment. Here we're flying into some smoke. And so in that smoke, the system has decide, hey, my SLAM system is getting bad. I have to get out of the way. The drones here have to be fully autonomous. There's no operator. So you have a team of those flying around because the drones are actually out of comp, right? It's inside a cave and it's really hard to have communications in there. So they have to just go out there, do their thing, and then come back. You can also see that the robots have to handle quite a wide range of situations. So for example, here you have some big open caves, narrow hallways, and so your algorithms have to kind of generalize for these situations. Now, if you and here you can kind of see some of what's happening under the hood. So it's basically building this map, deciding to plan. Here it's lining up to try and fly through a door, for example, and then explore the space, right? So the high-level goal is exploration. Here we're flying inside a cave, so it has to basically handle flying in these kind of dusty situations. And the robot has to be quite aggressive to be able to get into these narrow spaces, to be able to find people, find objects, and so on. So so a lot of what's going on under the hood here is not the focus of the talk, but I just wanted to kind of get you in the frame of mind of how do we, if we're in this kind of situation, how do we think about safety, and how do we, in the end, have guarantees for these systems, right? If you think about what would be some potential, this is all about pushing the technology forward, right? But in the long run, to think about, okay, if you really want to have these systems out in the field, how do we have some insurances, right? These could be, I mean, this is a former steam power plant that shut down, right? But imagine this is a high consequence environment, right? Like you're flying around in some nuclear power plant. Well, we did that too, but in some other environment, right? And so if you go to them and say, hey, my robot works great 90% of the time, then they're going to be like, okay, well, come back when it's 100, right? And so so we have to think about how do we build these safety cases. And so I just wanted to show you some ideas of some of the structure of how we're thinking about this, and then some ideas of how we're handling some of this. And so I'll kind of skip to the end here. So and so if you think about risk, it comes from the two different sources of factors, right? Known and unknown factors. And so you can have known unknown. So these are things that we don't know, right? So that we know that we don't know. So this is things like certainly in your SLAM system, there are known knowns, right? We know that we have to follow some rules, we have to handle some things, and we have to handle that. There's unknown unknowns, so there are things that we don't know and that we didn't think about. These are completely out of distribution, something that you as the designer didn't think about when you built the system. And there are unknown knowns, so there are things that we build into the system that are biases and would cause you to fail. And so I'll kind of try and give examples for each of these. But in the end, what we would want, if we want to deploy these systems, is to build a safety case for these robots, right? And so, UL4600 is one example, but there are different standards for different use cases, flying in cars and all this stuff, right? It's not like a given. But the idea is usually the same, right? So you build some safety case by building a structured argument of saying, okay, this is why my system is safe. And of course, there's a large set of this is related to, engineering your system well. But here I want to talk more about the kind of underlying fundamental system, hard parts of this argument. And so the way you build these safety cases is to say, okay, I want to claim something. How do I claim that? And then how do I show this, right? And so sometimes this can be done by design, right? You just design your system such that you can make that argument. Sometimes you run some tests. Sometimes you can do some formal verification. So any questions so far? All good. So let me give you kind of 4 examples for these claims. So one of them is to handle, and so there are different types of claims, and I'll kind of show you one example from each of these 4 corners in this quadrant, right? And so for this known unknowns, one of the methods that we are looking at is trying to model from large-scale data. For the known knowns, is trying to use explicit knowledge representations. Unknown unknowns is to use out-of-distribution scenarios, and for the unknown knowns is to monitor and mitigate against inherent failures. So I'll now show you kind of an example for each of these cases. So for the known unknowns, one of the strategies that we employ a lot is to try and formalize the problems and then help evaluate them with large-scale experimentations, data sets, and simulation. And I probably don't have to tell you, but robotics is becoming more of a large data science problem, right? So a lot of our progress is driven by these large-scale evaluations. And one of the things we observed is that there's a lot of work that relies on these small data sets, and that's okay if you don't have some machine learning method in your system. But once you add machine learning with a lot of parameters, you can't do that, right? I think the trend why we started doing a lot of our data sets back then was when we started seeing people developing, a lot of people in the room might know the Kitty data sets for SLAM algorithm development, right? And people are using, I'll train my algorithm on Kitty, and then I show my algorithm on Kitty, and it works great, and therefore everything's great. And we're like, no, don't do that, please. So that's where a lot of our work on these data sets came from. And since then, it has turned into its own area. So over the last couple of years, we've released a lot of different types of data sets. So for example, the Tartan ARV2 data set is kind of what kicked off a lot of this. It's a very large scale simulated data set. And there's a paired up data set that based a lot on some of the sub-T data set with ground truth, independent ground through survey scanners that you can use to do a lot of evaluation. In the upper right, is the Tartan Drive data set. So that's a lot of autonomous driving data that you can use for various use cases. And then in the flying domain, there are several data sets. One of the ones that's probably the largest that we have is the Amelia data set in the lower left-hand corner. So that's all the air traffic in the US is around the major hubs, so the largest 48 airports over the last 1.5 years, and it keeps on growing. And so that data set is quite interesting because you can see it's basically 1 hertz of all the aircraft movement, and so you can see actually lots of interesting things, even beyond some of the safety and it's one of the things we use it for is intent predictions. But even if you are interested in efficiency, for example, it's pretty interesting. And in the lower right-hand corner is a data set that we developed for aircraft tracking in all kinds of weather conditions with a large range of different aircraft types. Now, this is a stationary set of cameras, so we don't have the moving cameras, but we get a lot of environmental diversity and different types of aircraft. And there's other data sets that have more in-flight data, but not as many variations in the types of aircraft. Yes.
Is this Amelia data set available for public?
Yes. Yes, this is public. Yeah. It's about 70 terabytes, but a subset of it is available on Hugging Face. So it should be, and there's a really nice set of tooling available in Python to dig through it and do all kinds of stuff. And so our feed is roughly 5 minutes delayed, but then until the data is actually ready, available, I think it's usually like a day delay or something. So this keeps on building. We started in roughly 1.5 years ago. So a lot of fun stuff to do in that data set. And I mean, especially with all of these recent events right now, there's a lot of, unfortunately, there's a lot of interest. So let me show you a little bit of what we can do when we have that data set. So here we recreated a scenario that's similar to the scenario that was last year in January at Haneda Airport, where you have this kind of night situation. You have one aircraft on approach to land and the other aircraft trying to take off. The tower clears that first aircraft to take off with no delay, but that first aircraft's a little slow, and so doesn't take off right away. Right? So this is kind of a pretty typical situation that can occur. I mean, it's not that frequent, but it is. It's one of the scenarios that's pretty common. And you can also see how hard it is to detect other aircraft, right? Especially at night, you have the lights from the runway, and the aircraft has lights on it, but it doesn't stick out that much, right? So now, based on all observing the behavior of aircraft, we can build this prediction model, right? So we're predicting future aircraft movement, and then we can see if a situation develops, and then the system will call a go around, and then it can work, right? And the trick, the kind of game that you're playing in a lot of these systems is you don't want kind of false positives, right? In the Haneda example, they had a runway occupancy monitoring system, but the controllers just ignored it because it was always alerting, right? So because it's so busy and there's always somebody, so it wasn't as useful, right? And so this is this fine line that you're trying to play here, and a lot of this here comes out to anomaly detection. So another example here is what you can do with this type of data is if you have these known unknowns, then we can model the uncertainty. So for example, here we are deliberately degrading our SLAM system. So basically, here we are only using the LiDAR, and I knew it has more sensors. But then in this case, the fog was essentially so thick that it didn't have any LiDAR data. And so in that case, it can fall back to the IMU, and it's really about having a good sense of uncertainties to be able to then use those uncertainties to build a good SLAM system. Right? And so another situation occurs here in these stairs. You have this kind of partial degradation with narrow spaces where you don't have enough, and your gears here in the background. So with narrow spaces, your LiDAR isn't enough constraint to do good state estimation, and so you have to trade off between the IMU and the LiDAR. And so this is the kind of output you can get. You try to, if you do good modeling, so there's no loop closure here. This is just odometry. And we actually just recently open sourced that method also, if you're interested. You can just play with it. So just to give you an idea, yeah, the video is a little choppy here. And we might just quickly stop and try and see if I share. I think I might have to click the video button. Optimize the video. Sorry. Okay. Yeah, this is better. Okay. So to get a sense of the type of map that we can create. So now you know what happens at CMU campus at 2 a.m. Okay, here's just another example for in a similar idea. So here you have LiDAR, visual plus thermal, and so you have to be able to have a good uncertainty to be able to trade off these different modalities. Right, so here we're going inside a smoke-filled room. The LiDAR does not work. It only uses the thermal camera, and the visual doesn't work, right? And so then it basically goes back to LiDAR odometry, and then here it goes inside a hallway that's very narrow, and so then it switches to visual odometry, right? So you can kind of get these trade-offs, and that's what you can do when you have known unknowns, right? So you can do a lot of this uncertainty distribution. Let me give you some other recent things that we've looked at is to do IMU odometry, so no other sensors. And so here the idea is, again, we can use a lot of this uncertainty estimate to make our algorithm better. So I'll maybe do a little quickly here, but the idea is to say, what we saw in a lot of this prior work, so a little context switch just mentally. So in this setup, we only have an IMU, and we're trying to integrate it to do odometry on a drone, right? And so typically this is difficult because on a drone, we don't have things like steps or zero velocity updates to help you, right? And so what we had seen in a lot of the prior work is that it would try to get accelerations in the global frame and take out gravity, and then try to learn this motion model. And actually, that is not a good idea because you lose. So yeah, so prior work had looked a lot at this kind of global estimation, right? Just in a global frame trying to integrate. Instead, what we just changed is to body frame. So not very complicated, but it actually makes a huge difference in terms of what you end up being able to learn. So the top line, if you look on the right here, is what you get if you just do this global frame optimization. On the bottom is if you just switch to body frame. So just so I think a high-level message here is what we just having ML experience is not enough. Actually, knowing about robotics is a good thing. It transforms, and so don't forget that in the field of transformers alone. And so then, if we add this attitude encoder, which helps us with the gravity, we get another good improvement. And so if you put these things together, we can now build this whole IMU integration system that works very well. Now, one of the things that is also important here is that we additionally learn this uncertainty. So if you look here, the second blue box here at the bottom, that helps a lot with learning uncertainty, and that's when we fuse it together with an EKF, where we can put these together, that we can get a nice output. Now, the integration is based on a model called IMU. So this is a model where we combine some of the traditional integration with a network that also learns uncertainty. And again, this uncertainty learning is quite important. I'll skip some of the details here. And then now, if we switch gears a little bit to how could we think more about uncertainty in terms of the stereo odometry. Again, here, the key thing is to have good uncertainty estimates. Right? And so these then help you select good features that make your whole problem better downstream. And yeah, here's the result of Kitty, but it has never seen Kitty. Okay, cool. And so just some idea what this looks like. So when you put this together, the key here is really to be able to have good key point selection, and that helps you to do good advantage. Okay, cool. So just to recap, I showed you, I went a little fast here at the end, but the idea is really, if you know something about our uncertainty, incorporating that in your methods can really help you both in performance and robustness, right? So if you know that you will have some fog, you will be degraded, then you should think about this, right? And I encourage you, when you develop the algorithms, also to think about this, right? I mean, we're often very focused on performance and great clean data sets, but I think as roboticists, we can control the environment many times, right? So it has to work in a large range of cases. One more, any questions on this section? Yes.
So how do you choose the basic data that's meaningful based on the data that you select and the type of application for everything?
Right. I mean, I think what I'm building a specific safety case, I would say is very specific to your situation, right? And so, for example, if you had mouse-sized robots running around a conference, your safety case is like, would be nice if people didn't step on it, but otherwise it's fine. Maybe battery fire. So right, so you're just trying to work through this, which is different than, I don't know, my quadruped can fall down the stairs and fall on a work like this, right? Or it can fall on a pedestrian, right? So and each of these, like, there's a lot of nuance in the safety case. I think what I'm trying to show here is more the framework and what are some of the ideas that we have to build into our methods when we develop them to be able to later support that type of argument. So I'm not trying to argue a specific case because it's very tricky, right? Not of the nuance. Any other questions? Okay, cool. So the next part is, okay, how do we use known unknowns? So and so here I just want to give you some example, right? So when we say we have some rules, we know the system should follow, we can encode them into the system, right? What I'd like to show you here is that sometimes it's difficult to say to go from what we want the system to go to coming up with those rules, right? And so trying to explicitly write down these rules can be harder than giving the system some examples. So what we looked at here is, okay, can we learn these relations and predicates to be able to help come up with a set of rules on how to make decisions. So the system here has some inputs. So this is more planning domain, like planning. How can we learn these abstractions? And so one of the methods we came up with is this idea of doing this bi-level learning, where we are essentially expanding a tree and we are learning these predicates, see how these predicates agree with our demonstrations, and then use those predicates to see if they agree. Then we can add them as new things to plan with, and then we can actually repeat that step with this kind of expectation maximization paradigm. So this is how this looks like. And I think I'm running a little, how long do I have? 8 minutes. So I'll kind of skip some of this. But the idea would be, you can effectively, you have some demonstrations, you can see how consistent they are with what you're proposing. You learn some neural net classifier to see if that is correct in terms of the effects. If it is, you add it as a new predicate. Okay, and then so this is one example for the known unknowns. For unknown unknowns, we want to be able to degrade gracefully in out of distribution scenarios. And so here's one example of some of the work we did is where, let's say in this autonomous driving situation, if you have some fancy network that runs some planner, and we want to be able to say, hey, if you're in out of distribution situations, you'll fall back on a more classical method. And so what we want the system to do here is to learn a predictor that predicts higher pseudo counts or confidence in distribution situations rather than out of distribution situations. And so in out of distribution situations, we want to weight this rule-based planner. And so if you look at the results, if we're in distribution, your rule-based planner and the IL planner, have different actions, but it trusts the IL planner is inverse reinforcement learning planner more than the rule-based planner, and so the results look good. We switched to Singapore, which the system had never seen, and this is a little bit of an extreme example. You can see that the learned system performed very poorly, right? It's completely out of distribution, on a different side of the road. And so, therefore, the rule-based planner effectively takes over, and you get the performance of the rule-based planner, which might be less than what you get if you had more training data with your system, so you can see. So this is one example of how you could use unknowns. And so last, I just wanted to give an example for unknown norms. So, for example, here we have some use cases for autonomous off-road driving. So, for example, if you look at our test site here, there's a trash pile straight ahead, and it actually isn't. You could drive through this trash pile. We can recognize it as a trash pile because it looks very different than the rest of the trash site. but it is very high risk, right? Like who knows what's in that trash pipe, right? There could be metal in there, there could be some bottles, you know, whatever people end up doing at that test site. And so we want to be able to, you know, avoid that if possible. And so there's a lot of nuance in this kind of off-road decision making, right? Just because something is a trail doesn't necessarily make it traversable, you know, vegetation, all this kind of stuff. And so we have built this pipeline. I will not kind of go through the details of this, but the key part I want to take a look here is again that we're doing this uncertainty estimation. So if we have uncertain situations, we can choose if we want to go through this or not go through this. And then, so this is kind of what the features look like that we create when we build this this kind of map. So we have the this is the input to our system basically that it learns from, right? So this is a PCA on some foundation model features that we use for driving. And then we learn in that setup, we then take those to IRL on a lot of behavior of what we see. We also build these speed maps based on roughness. So this is self-supervised. So the system basically looks at the IMU and it says how rough it is the area I'm driving through. And if there's a lot of roughness, then you want to drive slower. So that it tries to match that, and that works quite well. And then the uncertainty estimation is how much out of distribution. Now, one of the things that will happen is that we know that, you know, we'll not be able to handle all these cases. So we want to be able to learn on the fly. So we're basically, as we run the robot on the fly, we're running some estimator to try and refine that system. And so since we have the uncertainty, we can refine the refine the cost estimate. Let's see. Okay. This is what the system looks like, and then this is, and so then we can, yeah, I think I forgot to show you the wrong slide. Anyway, so here you can just get a sense of what our system looks like. So we have on the top right, you can see kind of the raw features, and then in the view, you can see the actual cost map that's used for planning in the system. And so just get a sense of what this is. And so here's more the top-down cost map. So the actual mapping and cost feature calculations in 3D, but then we project it to 2D for the driving. Okay, cool. Yeah, so just to summarize, I think time good, right? So, when you're trying to have a safe robot, right, you have to build a safety argument. There are these 4 different categories of things you have to worry about. I gave you some examples from each of these corners, and you know, there's a lot of things to explore here. But maybe the high-level message is, as you're designing your system and as you're designing algorithms, maybe think beyond just you want high performance, but also how would that fit in if you actually wanted to show the safety of the system, right? And when you test, you know, try and test on hard cases as well and see how does the system degrade. Right? Thanks, everybody.